Hi and welcome to this Leaving Cert higher level maths video where we're going to look at the proof by contradiction, which is prove that root 2 is irrational. This is a paper 1 proof. We're going to use our formula and tables book on page 23 to help us with the start of this proof. In particular, we're going to use the definition here for rational numbers. So rational numbers are given by the letter Q, and they're where we have P divided by Q, where P and Q are both elements of Z, which means they're integers, and Q does not equal 0. So proof by contradiction, as its name may suggest, is we're going to try and prove the opposite, and when that proves to be untrue, we'll be able to prove what we initially wanted. So for example, here we want to prove that root 2 is irrational, so we'll start by trying to prove that root 2 is rational. Like I said, to help us, we're taking in this little piece from our log tables. So the first step is to assume that root 2 is rational. So if root 2 is rational, it can be written in the form of P over Q, where P is an element of Z and Q is an element of Z, and Q does not equal 0. That all comes from the log tables, and it can be written in words if you prefer, but it's given there on page 23, so you might as well utilize it. The final piece is that P and Q have no common factors. So what we are assuming here is that P over Q is in its simplest form. So P and Q do not have any common factors. P over Q cannot be simplified further. That's really key to this proof. So we're going to start with letting P over Q equal root 2. To get rid of that square root, we're going to square both sides. So we get P squared over Q squared equals 2. To get rid of that fraction, we're going to multiply both sides by Q squared, which gives us P squared equals 2Q squared. So 2 is a factor of P squared, which basically means that 2 can be divided in, which defines P squared as being even. And if P squared is even, the square root must also be even, which gives us that P is even. So what we're going to do is, now that we know that P is even, we're going to rewrite it to show that factor of 2. So we're going to write this as P is equal to 2K for some K. So because P is even, it can be written as 2 times some number. So we're merely splitting it into its factors of 2 and some other number. So if P is equal to this 2K, we can go back to our P squared equals 2Q squared and sub in for P. So what we get is 2K all to be squared is equal to 2Q squared. Expanding that, we get 4K squared is equal to 2Q squared. And then we're going to divide both sides by 2. I'm going to flip it so that Q is on the other side. And we get Q squared is equal to 2K squared. So by similar logic, since 2 is a factor of Q squared, we know that Q squared is even, and since Q squared is even, its square root, i.e. Q, must also be even. Now, this contradicts what we said at the start, because if both P and Q are even, then they would have a common factor of 2. And we've already said that if root 2 is rational, this cannot be the case. So we now know that, well, if P and Q are even, then 2 is a common factor, which contradicts what we've initially said, which means root 2 cannot be written in the form of P over Q, and therefore it cannot be rational. Instead, it must be the opposite, which is irrational.